Okay, so today we're figuring out if two lines are parallel or not, and if they're not, we have to state why. So really what it comes down to is let's set up both these equations in slope-intercept form so we can figure out what their slope is. Now, the first one, what we can tell is it's already in slope-intercept form, or y equals mx plus b. And what we notice is that the m is 2, so I now have a slope of 2. And I want to figure out what the slope of the second line is. So I'm going to take that second line, 2x plus y equals 8, and I'm going to rewrite it in slope-intercept form, which means for this one, all I need to do is move that 2x over. So I'm going to go ahead and add my 2x. I'm going to go ahead and add my 2x to both sides. So that's going to cancel out over there. And I'll have a y equals 2x plus 8. And now I can compare the two slopes. So I know that the two slopes are the same. So I know that they are parallel. And I know that they both have different y-intercepts, which means they're not the same line. These are two unique lines that are parallel. So they're parallel. For some reason, I wrote parallel with a T. Let's ignore that. And they're two separate lines. So parallel and two separate lines. Awesome. So let's do the same thing to the next one. It's as simple as just looking at it and saying, hey, this is already in slope-intercept form, so I'm looking for, will this have a slope of 3 or not? So the first thing I'm going to do is I'm going to move that x over. So I'm going to add 6x to both sides, which cancels that out. And I'm going to rewrite this right here, so 2y is 6x plus 10. And the last thing I'm going to do is I'm going to divide everything by 2, which isolates my y. So I get a y is equal to 3x plus 5. And so this, like the first one, they both have the same slope, so I know that they are parallel, this time with a t again. I don't know why I'm doing parallel like that. But I notice that we have a y-intercept of 5 and a y-intercept of 5, which means that if I look at this line and I say, hey, here's my x and y graph, and I have a 3x plus 5, it looks something like this. My next line has the same slope and the same y-intercept. So I'm looking at the same line. So parallel, and they are the same line. I'm not really sure what's going on in my writing today. I seem to want to blend letters together. So likewise, these are going to end up with your two different results of if they have the same slopes, two different lines mean they're separate. Two of the same y-intercepts means they're the same thing. The line by comparison that we had up here, we had one with an intercept of 6, and this one moved at the same rate, but it was a little higher up on the graph. So assuming that these were drawn perfectly, two parallel lines that never touch, two parallel lines that are right smack dab on top of each other. So what I want you to do is I want you to pause the video, try number 5, unpause it when you're done and see how you did. Okay, so let's see how we did. I had a slope of 1/2, and I want to compare that to what my next one's going to be. So I'm going to add my x. It's going to cancel that out. And I have a 2y is equal to x plus 14. Then I'm going to divide by 2, which leaves me with a y equals 1/2 x plus 7. And I'm going to compare my slopes. Oop, I know these are parallel. Parallel written correctly this time. But again, I have intercepts of 7, so I know that these are, just like before, they're going to be crossing through the same point. So parallel, and they're the same line. You could also call them overlapping, but I think overlapping sometimes gets confused with. People think that overlapping should be like this, but oftentimes people say, well, hey, if I have a line like this and a line like this, aren't they overlapping at that point? And technically, yes, they are, but we know that that's not what we want. Overlapping technically means that, but whatever. So let's go ahead and let's try one a little bit more complex. Now, the only difference here is that neither one of these is in slope-intercept form, which means that first what we're going to have to do is we're going to have to solve for the slope on this one. So negative 4x plus 2y is 6. I'm going to write that first one over here, and I'm going to write the second one over here. Negative 6x plus 3y is 30. I'm going to solve both of them separately. So add 4x, cancels that out. So 2y is 4x plus 6. Then I divide by 2. So we get y is 2x plus 3. So I'm looking for a slope of 2 on this one, and I want to see if we get anything remotely close to that. So I'm going to add my 6x. Cancels that out. I have 3y is 6x plus 30. Divide by 3. I get y equals 2x plus 15. So again, same slope, so I know these are parallel. Different y-intercepts though. So these aren't the same line, these are 2 different points in the graph, which means they're never going to touch. So parallel. And again, don't know what I'm doing with the last L in parallel. That's a P-A-R-A-L-L-E-L. Don't know why I'm doing it with a T. So parallel and 2 separate lines. Maybe I'm getting excited about the 2 and 2, and I don't know. We're just going to ignore that for today. So, perfect. So what I want you to do is I want you to keep that in mind. I want you to pause the video, try number 9, resume the video when you're done, and see how well you did. Okay. So we know that because neither of these are in slope-intercept form, I'm going to have to, negative 18, write out both of them. X minus 2y is negative 4. Okay. So I'm going to subtract my x on this one, which gets rid of that right there. And I'm left with a negative 3y is negative x minus 18. And when I divide by a negative 3, I know not only does it change the signs, but that becomes a fraction. So negative negative becomes a positive 1/3. Negative negative becomes a positive 6. So I'm looking for a slope of 1/3 over here. Let's see what we get. So subtract my x, gets rid of that. So I'm left with a negative 2y is negative x minus 4. So when I divide by negative 2, I get y equals, well, negative negative is going to be a positive. That's 1x divided by 2, so 1/2 x. Negative negative is going to be a positive 2. And so what I'm looking at right here is that our slopes are not the same, so these are not parallel. And that's all we can tell for right now. There we go. So today what we're going to be finding is the equation of a perpendicular line that goes through a certain point. Now, the big concept that what we have to remember from perpendicular lines, what we've covered previously, is that perpendicular slopes are what we call negative reciprocals. This comes from 2 different ideas. Negative just simply means that one's positive, one's negative. It doesn't mean that the perpendicular slope is always negative. It means we're going to change the sign. So if it was positive, we'll make it negative. If it was negative, we'll make it positive. This also means the reciprocal is their flipped versions of each other. So the idea of 1/2 and 2/1 or 2 are reciprocals of each other because we're looking at things on opposite sides of the numerator and denominator. So let's go ahead and take a quick look at what we have over here. If we're looking at a line that's perpendicular to y equals 3x plus 7 and contains this point, we need to first find our original slope. So this is in y equals mx plus b format. So I know that my slope is going to be the number attached to the x, 3. So what I'm going to do is I'm going to say, okay, if my original slope, m1, is 3, in fact, I'm going to even make this a fraction. My original slope is 3/1. My slope that I'm going to be using is going to be a flipped version, so 1/3. I flipped that upside down, and I'm going to change the sign. So I've reciprocated it. Now I'm going to change the sign. That was, let's see, 3/1 was a positive number, which means that my new slope is going to be a negative 1/3. And it's going to contain this point. So all that means is that I'm going to have to use my point slope formula. So y minus y1 equals m times x minus x1. Cool. So I'm going to say y minus, actually, let me go ahead and fill this out so we can do this a little faster. Y minus my y1 in this case is going to be an 8 equals my slope, which is -1/3, x minus my x1, which is going to be 3. Perfect. So I've got 2 steps to solve this. I'm going to go ahead, I'm going to combine these two by distributing. So y minus 8 is -1/3 x. Let's see, 1/3 of 3. Let's see, I know that negative is going to end up being a positive, and those 3's are going to turn into a 1/1, so it's going to end up being a positive 1 plus 1. Perfect. I'm going to add 8 to both sides. So I get y is equal to -1/3 x plus 9. There we go. Let's do one more version of that. I'm going to go ahead and I'm going to take my slope, which in this case is a -15, because it's in the original y equals mx plus b formula. And I know if my first slope is a -15/1, that means the slope that I'm going to use is changed. So m2 is positive, flipped 1/15. I'm going to use that slope. I'm going to plug it into my y minus y1 equals m times x minus x1 formula. So I get y minus x minus. In this case, my y1 is a -7. My x1 is a 30. And my slope that I'm using is a 1/15. Now it's positive, so I don't actually need to draw the sign. I'm going to distribute this 1/15. I'm also going to notice that double negative means that y is actually plus 7. So a 15th of 30/1. I know that those reduce. 30 divided by 15 is 2/1. So 1 times 2 is actually a 2, or just 2. So 1/15 x minus 2. Perfect. Keep this going, I'm going to subtract 7. Cancels that out, so I have y is equal to 1/15 x minus 9. Perfect. And so this one's already set up in a fraction for your original slope, so I want you to go ahead and pause the video real quick. Try out number 5 and see how well you do. Unpause the video when you're done to see how you did. Okay. So I know right here I have a slope of 1/2, and it's a positive 1/2. So I know my new slope, if my first one is positive, this is going to be a negative. And I flip it, so -2/1, or just -2. Don't need to put the over 1 if I'm just finding the equation. Okay. Plug it into my formula, and I get y minus, let's see, my y1 in this case is 16. My slope is -2, and my x1 is -4. Okay, so my first notice, especially if I have minus and negative, it turns into plus a positive. And so let's see what we get. -2 times x is -2x. -2 times my newly positive 4 is going to be a -8. Okay, in this case I'm going to add 16, which means y is equal to -2x plus 8. Boom. There we go. So let's try one. Now these next two are going to be, I guess you'd call them challenges. I have a 3/4. It's not a whole number. It's not a simple fraction. It's going to be a little more of a challenging fraction, but no worries. I know if my original slope is a positive 3/4, I know my new slope is going to be a negative 4/3. I'm going to flip it. Can't actually reduce that, so I'm just going to go ahead and plug it in. So y minus my y1 of 16 equals the slope, negative 4/3, x minus x1, negative 24. First thing I notice is minus a negative. And I'm going to go ahead and I'm going to distribute to my newly positive number. First off, negative 4/3 times x is just negative 4/3 x. This is the part that's curious. So my negative 4/3, so negative 4/3 times my newly positive 24/1. I'm going to go ahead, I'm going to cross reduce. So 24 divided by 3 is 8/1. So it's actually negative 4 times 8, which is negative 32. 1 times 1 is 1, or just negative 32. A separate way to look at that is saying, okay, 24, I'm looking at a fraction right here. I could say that 24, 4/3, I'm multiplying and dividing. Why don't I just take that in two separate pieces? So I'm going to divide first. So 24 divided by 3 is 8. And then 8 times negative 4 is negative 32. We are both dividing and multiplying. Dividing and multiplying is just a way of showing a fraction. Negative 32, negative 32, boom. Brings us to our last step. Y is equal to negative 4/3 x minus 16. Perfect. And the last one, having a decimal, is what could be the most difficult. So take a second and see how we would find a perpendicular slope to negative 2/10, or negative 0.2. Think about how we do that. Unpause the video when you're done. See what our solution was. Okay, so what happened is I may have given it away when we read what this number is. If we remember way back when in like elementary school, we know that, let's say a big number like this, we know that this is what we call the ones, this is what we call the tens, this is the hundreds spot, this is the thousands, and it keeps going up and up and up. We know that anything after a decimal is what we call the 10th. The next one is the 100th. Now, this doesn't actually just come out of nowhere. This is how the fraction is set up. So what I know is that I'm actually dealing with a line of y equals negative 2/10 x plus 1.5. So I have something that I can flip. So if my original slope is negative 210, let me actually write this out. Then I know my new slope, first off, if that was negative, my new slope is now positive. Flip it, 10/2. 10 divided by 2 is 5. So my new slope is actually just a 5. And I'm going to take my new slope, my point, plug it into my point slope formula. Y minus my y1 is negative 15. X minus my x1 is 10. My slope right here is positive 5. So I do two things. I notice that minus a negative becomes plus a positive, and I go ahead and distribute the 5. So 5x, 5 times negative 10 is negative 50. So we get y is equal to 5x minus 65. And there we go. So today we're going to be learning how to do polynomial arithmetic. Now, this usually means that we're dealing with distribution. So each term in one polynomial gets multiplied by each term in the other. This is most often introduced with the concept of foiling. I'm not going to show that in this video simply because foiling works really well when it's 2 by 2. Doesn't work if we're doing anything like a 2 by 3. It doesn't work on 3 by 2. Doesn't work on 3 by 3. So it's a very limited concept, although it is a very useful tool for introductory distribution of binomials. So let's take a look at what's going on. Now, with polynomial distribution, we only multiply the immediate term outside. With this addition sign, what that means is that this term, with this addition sign means that this term is not immediately outside the parentheses, so therefore we don't consider it. We only consider what's immediately outside. And in this case, that is an invisible 1. So we're actually going to distribute this 1 to each of these terms. We get x squared times 1. We get 7x times 1. Neither of them change. And because nothing is distributed over here, there's no terms to combine inside, we're going to simply drop the parentheses on the other one. 6x squared minus 5x plus 2. Then the only step that we have left is we are going to combine the terms. Now, we're going to combine them in what we call standard form, which means we're going to list them in alphanumeric order. I'm going to find my largest exponent, squared, and I'm going to combine them. 6x and x make 7x. Then I move down a power. I move to my single x terms. Negative 5x and 7x, when I combine them, I look at their coefficients. 7 minus 5 gives me 2. And then I include the variable. My last term is a 2. Boom, that's it. Now, similar to what we saw up top, I know that with an addition or a subtraction sign, I disregard the first term. I only deal with what is immediately outside the parentheses, which is a negative 1. And I'm going to distribute that to each one of these terms. All this does is, in effect, is it changes the sign. Positive becomes negative, negative becomes positive, positive becomes negative. And because there's nothing to distribute on this side, I simply drop the parentheses. Boom. And then at this stage, the only step left is to combine terms in alphanumeric order. So I take our cubes, so 4 minus 2 is 2. I move down to the squareds, so I have negative 3 plus 4 gives me a positive 1, or just a positive r squared. I don't need to draw the 1. The next term is my negative r. My last one is my minus 5. And there we go. So again, we're only distributing what's immediately outside. What we see that's immediately outside on the next two are another set of parentheses, which means that this negative 6 is immediately outside and this 7x is immediately outside, which means that we're going to have to do this up here, not once, but twice. Once for the 6, once for the 7. So let's do that. Let's distribute the negative 6 to both of these. So negative 6 times 5 becomes negative 30x. Negative 6 times positive 6 is negative 36. And so now that we've distributed the 6, let's continue on and distribute the 7, because that gets multiplied times both of these as well. 7 times 5 gives me 35. I have 2 x's, which means x squared. 7 times 6 is 42, and a single x. There we go. So now the only step that we have to combine these is, again, to list it in alphanumeric order. I have a 35x squared. I have a negative 30x and a positive 42x. Is 12x. The last thing that I have is going to be minus 36. And there we go. And that's really all it takes. The last one that we have right here is a little misleading. One of the things that I commonly see students do is they see the squared term, they see the parentheses, and they immediately think, oh, let's distribute that and let's square 3m to 9m squared and square the negative 1 to plus 1. And they're like, hey, that was easy, and I'm done. Well, remember, we're not going to do that way. Because albeit that is an intuitive way, why don't we just distribute that square? That's not how it works. Because remember, with a squared term, that means we're multiplying this times itself twice. So let's write it out twice and see if it changes how we approach it. Well, 3m minus 1 and a 3m minus 1. So that looks like I'm going to have 4 terms, not 2. So let's go ahead and let's start the distribution process. I'm going to distribute that negative 1 to both of these. So I'm just dealing with the first term. Negative 1 times my 3m is negative 3m. Negative 1 by negative 1 is positive 1. Then I only deal with the 3m. So I say, okay, what is 3m times 3m? That is 9m squared. Then what is 3m times negative 1? Negative 3m. And so I know that my final answer after I combine like terms is going to be 9m squared minus 3 makes minus 6m plus 1. So similar to what we would have assumed, but we would have missed the middle two terms. So out of, if we went with FOIL, F-O-I-L, we would have forgotten about the O and the I, and we would have just done F-L. And so again, because this video was originally made in Florida, we're going to call that the Florida method. Don't be Florida man. So let's take a look at some other problems. And this is where FOIL tends to break down. Because with this, I have first, outer, inner, last. We notice that we never distribute to this negative m. First, outer, inner, last. Well, then why even include the negative m if we're going to skip it? So again, that's where FOIL doesn't work. So what we're going to do is we're going to distribute the first term, the positive 2, and then we're going to distribute the next term. So let's start with the positive 2. We get a 12m squared, 2m, a positive 4. The next term that we distribute is my 4m. 4 and 6 make 24. And I have 3 m's. 4 and negative 1 make negative 4. I have an m squared. 4 and 2 make 8. So that our final answer, we just go from the highest exponent to the lowest exponent. Boom, and that's it. The same thing applies to this. This was a 2 by 3. This is going to be a 3 times 2. So let's go ahead and let's see how that would work. Well, the 3 by 2, I'm going to distribute my negative 6, which gives me a negative 12x plus 24. I'm going to distribute my negative 6x, negative 12x squared plus 24x. And then last, I'm going to distribute my 7x squared. I get a 14x cubed, and I get a minus 28x squared. And so albeit I had 3 terms, I need to distribute 3 numbers to 2, so 1, 2, 3. And so when I combine my terms, I start with the highest exponent of a 3, 14x cubed. Move down to the x squareds. Negative 28, negative 12 give me negative 40. Move down to my single x's. 24 minus 12 gives me 12x, and my constant. Perfect. And so we got the idea. Whether it's 2 by 3 or 3 by 3 or 3 by 2, it's going to work the same as the following two questions. Let's take a look at what a 3 by 3 problem would look like. Oh, we're going to distribute our negative 5. Let's get a negative 35y squared, negative 30y plus 25. So I distribute the 5 to 3 terms. Boop, boop, boop. I have my 3 answers right there. Next up, I'm going to distribute my 6y, or my negative 6y, to all 3 terms. So I should get another 3 right here. Negative 42y cubed is 36y squared plus 30y. Awesome. My last one is distributing the 6y squared to 1, to 2, to 3. I might run out of space here. So I got 6y squared and 7y squared, and that's 42y fourth. 6 times 6 is 36y cubed minus 30y squared. So I noticed that this equation, or this expression, goes on for 2 lines. And now this is where it might get a little confusing. The math isn't difficult, but keeping track of your terms can be. So that's why we always list it in highest. I only see 1/4, so 42y to the 4th. And what you may want to do is either lightly or gently scratch out your term so that you know which ones you've already dealt with. After the 4th, I'm going to go to the 3rd. 36 minus 42 is going to give me a negative 6y cubed. And again, I'm going to very lightly scratch that out, so I know I'm not dealing with that anymore. I have y squared, y squared, y squared. So negative 36 and negative 35 make negative 71. Minus 30 is negative 101. And again, very lightly scratch them out. Last thing when I'm dealt with, plus 30y minus 30y. Those actually cancel. So I have no y term. I'm left with 25. There we go. And so this combined rather nicely. Sometimes with questions we get ones that don't combine rather nicely, but the math is going to be the same. So try this one. I'm going to work it for you. I'm going to work it silently, so that way when you look up, you might be able to check to see if you've done it correctly. So that one was fun. We had all these terms, and at the end, we didn't get a lot of them to combine. We mainly just listed them in the proper order. So that's how we do polynomial arithmetic. So today we're going to be going over polynomial identities. These are things that we've already learned how to do by hand, but we're going to learn a few quick and hard set rules that we can write down so that we can do problems like these in one step without having to show any of our work. So the whole reason of studying identities is, again, we know how to do the long form of these, but if we plug in some generic numbers, so numbers that I can replace anything with. So like, I'm going to take my 6r and I'm going to assume it's an a, but what happens if it's not a 6r? Would it still work? Well, let's go ahead and figure out what we would do. So if I have an equation like a plus b squared, that's telling me that I have a plus b times a plus b. I am going to distribute my a to both terms. So I'm going to get a times a, which is a squared, a times b, which is ab. And then I'm going to go ahead and distribute my b to both terms. I have b times a, and then I have b squared. Well, I notice the fact that these two middle terms, it's ab, and basically this is ab, it's just backwards. So I can combine those. There's two of them. So I have a squared plus 2ab plus b squared. And this is our first polynomial identity. It's a plus b squared. So what we've got going on is the fact that if we ever see a perfect square trinomial like this, I know I'm just going to square the first term. I'm going to square the last term. And then I'm just going to multiply the two numbers together and double it. So if we have a sample problem like this, without having to do any work, without having to show our steps, we can just say, hey, I'm going to square this first term. 6 squared is 36. R squared is r squared. I'm going to square the last term, so I'm going to get a w squared. And then in the middle, I'm going to multiply the two things together. 6rw times 2 is 12rw. And boom, we knock it out with no steps. So another polynomial identity is the fact that let's reverse that. So with a perfect square trinomial, what we notice is that we have a perfect square in our first term, perfect square in our last term, and we have double the product, basically this thing right here. But this is typically how we're going to see it. We're going to look at it and we're going to say, hey, I recognize that I have a squared number and a squared variable, and then I have a squared number. And I'm going to look at the number in the middle. I'm going to say, hey, if I take the square root of each end, so that 25, if I take the square root of it, that 49, if I take the square root of it, multiply them together and double it, is that what I see? So the square root of 25 is 5. Square root of 49 is 7. So 5 times 7 is 35. Double it is 70. Yes. This is going to check off for what we're about to do here. So how do we factor this without having to list a set of factors of whatever 29 times 4 or 25 times 49 is? Well, let's factor this one so we can create a rule for every single one of these. So if I have some number, we know typically the way that we factor is I'm going to take the constant and multiply it times the constant, or I guess the coefficient, multiply it times the constant. So I'm going to say AC, or a squared times c squared is going to be a squared c squared. And I'm going to try and find a set of factors that, because this is positive, that make a sum of 2ac. Okay? So what two numbers? Well, what I could do is I could say a times ac squared. I could say a squared times c squared. I could say a squared c times c. There's a bunch of different possible factors that I could have, including, if these were bigger numbers, any possible sets of factors that they come up with. But the one that we're after right here is going to be ac times ac. Because ac times ac is a squared c squared. And if I add these two together, I get 2ac. So I know how I'm going to split that middle term up. So I'm going to say a squared plus x squared plus c squared. I'm going to split that middle term into basically ac, ac. Okay? And then I'm going to create a factoring by grouping. I am not sure why I put a plus sign right there. That is going to be a times sign. A squared, x squared. I'm not going to suddenly introduce an addition problem. I'm going to take the GCF out of each one of these. The GCF over here is going to be a, oh, hold on, again. My AC, each of these ACs has an x, because it's ACX plus ACX equals 2ACX. So I'm going to pull out an A because they both have an A, and an X because they both have an X. Over here, I'm going to pull out a C, which means if I pull out an AX and a C, what's left over? If I take away an A, I have an A. Take away an X, I have an X. Take away an A, I have a C, and I don't have an X. So AX plus C. If I take away my C, I have an AX. Take away one of the C's, I have a C. And perfect. What I notice is that yet again, I'm going to do this one in red. I'm going to have an AX plus C that I can pull out of that. So I have AX plus C times AX plus C, or AX plus C squared. And so this is my second polynomial identity, which is just the flip side of this. We have our AX plus C, our A plus B squared. In this, we're just showing there may be a variable attached. So let's take a look at this. Okay, if I know that I can take the starting form and convert it all the way to the end, I'm going to say, okay, I need to find the square root of that number. So the square root of 25 is going to be 5. I'm also going to take the square root of that variable, x. Square root of 25x squared is 5x. And then I'm going to need to take the square root of that number on the end. 49, that's going to be a 7. And because this was a positive, I'm going to include it as a positive. Boop, boop, squared. There we go. No steps necessary, because we've proven that it works for any combination that follows this pattern. So let's do another type of factoring and foiling combinations. If I have a difference of squares factoring, I'm going to do the same thing that we just did right here. I want to come up with a rule. If I ever see a set of factors like this, I notice that everything's a perfect square and everything's a perfect square. Can I come up with a hard and fast rule to where I don't need to show a bunch of steps? Because as of right now, I'm going to have to multiply 49 times 64, like we did up here. And that's going to be a really big number to make a list of possible factors. So let's see if we can't speed that up a bit. Okay. So what we need to do is I need to multiply the first one times the last one. I notice that I don't have a middle term. So my middle term must be a 0. So 0ab. It doesn't exist. But I'm going to take a squared and b squared, and I have an a squared, b squared. Pretty simple. And this time, because it's negative, I need a difference. I need them to be separated, or taken the difference of that 0 term, that missing term. And so again, I could go through the entire list, but I bet you if I do AB and AB, AB minus AB is going to be 0. So that's exactly what we're going to do. We're going to take our a squared, and I'm going to add an AB, and I'm going to subtract an AB. Because AB minus AB is 0, so I didn't actually change that. I just introduced this arbitrary thing. I'm going to factor out the GCF of both sides. See, I have an A over here. I have a leading coefficient of negative, so negative. B in both of those. So I'm going to pull out an A and a negative B. That's going to leave me with an A plus B. Over here, it's going to leave me with an A, and it changes the sign, plus B. Hey, so I can divide out the A plus B. So I have an A plus B that I pulled out, and I'm left with an A minus B right there. So there's my third polynomial identity. If I notice that I have perfect squares on both sides and there's a different sign between them, I can just spit out this quick and hard rule and say, okay, I'm going to take the square root of 49x squared, which means I square root both of these, which is going to be a 7x. And I'm going to square root the last thing. So 64 and y squared, well, that's going to be an 8y. And I'm going to add it, and then I'm going to write it again with a subtraction sign. Boom, 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 boom. No steps necessary. There you go. The last one. The last one right here. Again, when I see that I have two 10s and two 2i's with different signs between them, I wanted to see if I couldn't come up with a hard and fast rule, which we'll see that, hey, we're going to end up reversing this. So let's take a look at how we work this. I'm gonna multiply my a by distribution, so I get an a squared minus ab. Then I'm going to distribute my b, so I have ba, or I'm just going to rewrite it as ab, and then minus b squared. I notice that these middle two terms, they're going to cancel out. So I'm left with a squared minus b squared. So again, I showed that I can FOIL this. Basically, I can FOIL this and end up back with this. And this is my last polynomial identity. So if I ever see something that's plus and minus, I'm going to say, okay, I'm going to square the first thing, 100. And I'm going to subtract, square the second thing. So 2 squared is 4, I squared is I squared. Except for this one, we're not done. Because with this one, remember what I squared is? If I is the square root of -1, then I squared is a square root of -1 squared, or just -1. So that's actually 100 minus 4 times -1, which is plus 4. So it's actually 104. And this is a big thing that we're going to be seeing coming up, is conjugates with lateral numbers, or conjugates with any sort of complex numbers. And there we go. Some official polynomial identities.